Hi, this is the second of two presentations offering you some design hints to simplify the development of this capstone project. At the end of this presentation, I expect that you will be able to create a block of RAM or ROM memory and add it to the minimal CPU project. Likewise, I expect that you will be able to create a top-level description for the CPU with external memory and to synthesize and simulate the operation of this CPU plus memory architecture. The presentation is organized into three parts, starting with the addition of a ROM block, then the addition of a RAM block, and finally some ideas that you may be interested to consider for expanding your work. Let's start by the CPU with ROM. This slide shows the already familiar minimal CPU architecture to which I have added an external read-only memory block. Notice that it is read-only because the data bus, represented in gray, can only transfer content from the memory to the CPU. I have also assumed a predefined memory content starting with the instruction code for loading the data register, which uses the first two memory positions, followed by the instruction code for incrementing the content of the data register, and followed by a jump instruction that redirects the program execution to an address that is specified immediately ahead of the jump instruction code. You are familiar with the VHDL description of the CPU architecture, so we will skip that part in this presentation. What you see in this slide is the VHDL description of a ROM memory block containing the program code for the following sequence of instructions. Load the data register with 55 in hexadecimal, increment the data register, increment the data register, and jump to 07 and finally halt. Notice that this memory block was defined as an array of standard logic vector types. We now have two VHDL design files, one for the CPU and the other one for the memory. We need to create a top-level description to put them together, as shown in this slide. The generic technology model created by Vivado is shown here. You can see the ROM and the CPU and their interconnections created as expected. We are now ready for the design verification of the complete architecture, including external ROM, and the program stored in memory for this purpose is repeated in this slide. Notice that the sequence of instructions is shown on the left, and the corresponding content in memory is represented on the right. Some instructions take up two memory positions, while others take up only one position, as you already know. This slide shows the simulation results. Please pause the video for a moment to check the sequence of states, comparing what happens in each case with what was defined in the complete ASMD chart. Notice the moment when each instruction takes effect. The data register is loaded with 55 hexadecimal at 35 nanoseconds, and then it is incremented at 55 nanoseconds. Why are these operations taking place as we move from state all 1 into state all 0? This second slide with simulation results corresponds to the same session but provides additional waveforms to enable the visualization of further details. You may pause here for a moment if you want to compare the current and the next values for the various registers represented. Let's look now at the case of the read-write memory. This slide shows the VHDL description for the RAM block, which is done differently from the other type of memory, although it was again created as an array of standard logic vector data types. Please pause for a moment and compare the descriptions shown for the two types of memory. What you see here is the top-level description comprising the CPU and the RAM unit. After successful synthesis of the top-level description, Vivado creates the generic technology representation shown in this slide. Notice that in this case we have two buses between the CPU and the memory, since the read and write operations were made possible by a dual-port data memory block. Just to make sure that the previous code continues to run as before, I have chosen to redo the simulation with the same test program. This means that the memory content will be the same as shown in this slide. You can see that the simulation yields the same results, and again at 55 nanoseconds the data register is incremented for the first time. Let's now check the new functionality enabled by the RAM block. I have chosen to replace the jump instruction by a new instruction that loads the memory from the data register. It takes two memory positions, opcode and target address, so we need to replace the content as shown in red in this slide. We are going to write in position with address 7, which was used as the destination address in the previous jump instruction. So all we need to do is just to replace the content of the position that holds the instruction code. This slide shows the new simulation results, and you can see that everything continues to happen as before, except when the new instruction starts to execute at 85 nanoseconds. At that moment, the write enable output will go high, and you can see in the waveform at the bottom that the current content of the data register shows up in the memory position with address 7 at 95 nanoseconds. How can you go further? You may, for example, consider the addition of logic and arithmetic instructions and eventually of additional data registers to support them. And you may as well consider the modification of the top-level description in order to comprise the simultaneous existence of the two types of memory, ROM and RAM. And keep in mind that your imagination is the limit, so you can add whatever new things you are able to think of. And that's it for the design hints in this capstone project. Thanks for your attention.